Hello, welcome back. Continuing our discussion about telescopes in chapter 7 of the OpenStax astronomy textbook. And we're interested now in addressing the question of why would you put a telescope in space? I mentioned it in the last video. It's much cheaper to build a telescope and put it on the ground, like orders of magnitude. The Hubble Space Telescope, launched in 1990, cost $2 billion. The James Webb Space Telescope that just launched last year cost over $10 billion, whereas the largest, you can build a 40-meter telescope for way cheaper than that. Hundreds of millions of dollars will get you a 40-meter telescope on the ground, right? Which is a huge increase in the light gathering power and everything else. And I mentioned one of the benefits originally of putting the Hubble Space Telescope in space was that it was above the atmosphere to get above the blurring effects of the atmosphere. And that's what made it revolutionary at the time. But as I also mentioned last time, we've sort of overcome that problem. Adaptive optics gets you almost as good as if you were above the atmosphere in terms of the blurring effects of the atmosphere. So why are we still building space telescopes? There's another fundamental reason why you have to do it. And that's summarized in this cartoon version of this plot. So what you're seeing here is the electromagnetic spectrum on the x-axis, from radio to infrared to visible to ultraviolet to X-ray to gamma rays, sort of all of the wavelengths of light that you could think about. And on the y-axis, you've got how easily that light penetrates our atmosphere. Right? So here is in the visible part of the spectrum. Why are our eyes optimized to see in the visible part of the spectrum? There's two reasons. One is that's where most of the sunlight, the sun is generating most of its energy. But the other reason is because there's a window in the atmosphere where the atmosphere is perfectly clear, and it happens to be for visible light. And so if you're building a ground-based telescope to look at the visible light, you put that on a mountain, you're doing just fine. You're not losing any photons in the atmosphere. Radio waves also pass very easily through the atmosphere. Almost all of them that reach the upper atmosphere will reach the surface, and you can detect them with your telescope. That is not true in any of the other regions of the spectrum, right? In infrared, most of the photons in the infrared that hit the Earth's surface get absorbed by particles and gas in the atmosphere. And so if you want to build an infrared observatory, you need to build it really on a really high mountain, or put it in an airplane or something, just so that you can get most of the photons before they're absorbed and are lost by being absorbed in our atmosphere. And this is why we put some infrared telescopes in space, because if you try to put one on the ground, you're going to be losing 90% of your light or something like that. It's even worse in the ultraviolet. Now, and it's bad in the X-ray, and it's bad in the gamma rays, right? This is all very good. This is all very helpful for us, right? We don't want to be inundated with gamma rays and X-rays from outer space in our everyday lives, because those are harmful photons. Those will cause things like cancer and mutations, and if they hit your cells. And so it's our atmosphere is protecting us from these harmful radiation, high energy radiation photons. But if you want to observe what the universe looks like at those wavelengths, and we do, you can learn different things about the universe in X-ray than you can in gamma ray, than you can in ultraviolet, than you can in visible. And the Hubble Space Telescope was a visible and ultraviolet telescope. It was optimized to be able to see in the near ultraviolet and in the visible part of the spectrum. And so the James Webb Space Telescope has often been billed as a replacement for Hubble. It really isn't. It's an infrared telescope. It's really a replacement for the Spitzer Space Telescope and the Surf Space Telescope. This is an old image. There are some other satellites that are in these wavelength ranges that have been launched since then, but it's a replacement for this and not a replacement for this, because it's an infrared optimized telescope. And in fact, you don't really need a space-based visible telescope anymore, because the ground-based telescopes with adaptive optics do pretty much as well as a space-based visible light telescope would do. Now, the thing that Hubble can do, that the new, and it's only going to, Hubble probably won't be around for much more than a few more years. When it finally dies, the thing that will be missing from the catalog of things that we can do is an ultraviolet telescope. And there's some interesting things that you can do in the ultraviolet that you can't do in the visible, the infrared, or the X-ray, the gamma ray. And that functionality, once Hubble finally gives up, will be lost, and we'll need another telescope at some point to try to replace that functionality. Anyway, there's lots of other telescopes up there. The Chandra is an X-ray observatory. The Swift and Integral are gamma ray telescopes. There's no way that you could observe and study the universe from the ground at X-ray or gamma ray wavelengths. It just isn't possible. And it's far better to get into space if you want to study it in the infrared as well. So that's the real reason to put telescopes in space. Excuse me. It gets above the blurring effects of the atmosphere, but you can correct that in other ways. The real thing is we have no way of seeing any of these photons from the ground. If we want to observe the universe in these other wavelengths, and we do, then we need to put those telescopes in space. So just a quick note about why are other wavelengths important. Let me just show you this image real quickly. Here is Orion, the constellation Orion. I don't know if you can recognize it because it's got these orange lines through it, but there's the belt. There's the red star on top, Betelgeuse. There's Rigel. This is the sword of Orion. This is actually Orion Nebula. And so this is a visible light image of what, when you look up in the sky and see Orion, you will see. That exact same region in the infrared looks completely different. Here's what that image looks like in the infrared. You can sort of see this entire region, in fact, this entire part of the sky is a giant star-forming region. And there's all kinds of nebulosity and dust that glows in the infrared in a way that it doesn't in the visible. And so you can see the Orion Nebula, you can see some other nebulas over here. These are star-forming regions. You can see that these are just the brightest of what is a huge complex of cool hydrogen gas that's being heated up by some very young, bright stars that have been formed in these particular regions in the area. But it's all sort of connected in this gigantic web of hydrogen gas and dust. And so you learn much different things in the infrared in this region than you do in the visible. And this is an X-ray image of the same region, and it looks completely different again. In fact, you wouldn't even recognize it as the same field, but it is exactly the same field because you're seeing completely different objects, right? You can sort of see that object and that object and that object are kind of the same, but almost nothing else matches up. These are completely different objects. These are things like white dwarfs and neutron stars and other very energetic things that are going on in the universe that we can learn about from the X-ray that you can't learn from the visible or the infrared part of the spectrum. So I just wanted to show you, why is it important to observe at different wavelengths? Because you learn completely different, new and interesting things about objects in the universe when you do detect photons of vastly different energies. Okay. We know that the Hubble Space Telescope has been up since 1990, but this is the most exciting new toy on the astronomical playground. The James Webb Space Telescope launched a little under a year ago and has been in operation for several months now, taking some of the most spectacular images you've ever seen. And this is, again, not a visible light telescope like Hubble is, but it's optimized and its instruments are set up to work in the infrared. And you need these extremely effective heat shields to shield it from the sun and to keep all of the instruments cold, because as you know, things that have a temperature like us are glowing in the infrared. And so if you want to be able to observe objects in the infrared, you need to keep the glow. It's sort of like light pollution. You need to keep the light pollution of your own telescope to a minimum. And so this is a heat shield. In fact, several layers of heat shields to keep all of those energy from the sun from reaching the instruments and the mirrors, to keep the noise, to keep the infrared background as low as possible so that it can observe some of the very faint things in the universe that it wants to try to observe. This is an artist's rendering of what it would look like in space. This is an actual image of the mirrors before it launched in the clean room at a NASA facility. And it's now operational, it's in space, it's doing its thing. And we've already seen many images on APODs this semester taken from the James Webb Space Telescope. It is much bigger than the Hubble Space Telescope. I just wanted to, we saw this on the last slide of the previous lecture video, but I wanted to show you this in more detail. This is the Hubble mirror. It's about 2.5 meters in diameter. It's about 10 feet or so in diameter. Little less than 10 feet. I did my math wrong. But you get the idea. The Hubble primary mirror, here's a sort of standard sized person. 2.5 meters is bigger than a standard sized person, but it's much smaller than the James Webb Space Telescope primary mirror. And it's 6.5 meters in diameter. And it's got the same hexagonal shape that the Keck telescope has. And it had some crazy unfolding things. Watch I'll post some videos to the James Webb Space Telescope site that shows some videos of how all this worked. It's pretty amazing because they had to fit this in a rocket that was much less wide than 6.5 meters. And so they had to do some folding and unfolding once they launched it up to actually get it in the rocket and get it into space. So the light gathering power of this telescope as opposed to this telescope is a factor of 7 or so. If you take this divided by this and square it, you get over 7 times more light gathering power for this telescope than this telescope. Plus, it's optimized for a different wavelength regime. We've seen some of that already, but let's take, this is the same image, the same region of space, and it's the Carina Nebula, I think, taken from the Hubble Space Telescope and the James Webb Space Telescope. And both of these images are stunning. I don't want to take anything away from the Hubble Space Telescope image. It's amazing. But the resolution and the detail that you can see in the James Webb Space Telescope image is far superior. It's unbelievably better. And not only that, you're seeing different kinds of things because this is an infrared image now, and this is a visible light image. So instead of this being just a dark knot, you're actually seeing some emission from parts of that dark knot and some reflection as well from other bright stars in the region. Anyway, just a stunningly beautiful and detailed image of a molecular cloud complex that is, again, actively forming stars in the Carina constellation in the southern hemisphere. I just want to, the NBC News did a great job of putting together the site, and I want to show you how this works. Here is that site where they allow you. I put a link to this in the canvas. Allow you to scroll back and forth between these two. For instance, here is I think this is the Southern Ring Nebula from the James Webb Space Telescope and from the Hubble Space Telescope. Right, both amazing images. But you're seeing actually better resolution and a lot more detail in the Webb telescope image than you are in the Hubble Space Telescope image. And you're seeing slightly different things because this is an optical vision version of this planetary nebula, and this is a infrared vision of this planetary nebula. Planetary nebulas have nothing to do with planets. They're sort of stars like the sun that are on their last legs and expelling their outer envelopes into space. And they create these beautiful nebulas for hundreds of years. Here's a series of galaxies. Again, Hubble Space Telescope on the left, James Webb Space Telescope on the right. You just get better detail and different information with Webb than you do with Hubble. Here's another, I mean, if you're interested in this kind of stuff, take Stars and Galaxies, but you can see how much brighter and clearer the image looks with Webb and its infrared camera than it did from Hubble. All right, so there you go. And for some reason, the Carina Nebula one isn't coming up. Oh well. All right. So that ends our discussion of telescopes. I think on Monday we will be ready to come in and start actually talking about objects in the solar system and how the solar system was formed, and we can move on to the meat of the class, talking about solar system objects themselves. Okay, great. I hope you have a good weekend. I hope I'm feeling better on Monday and can be in class. And I will hope to see you then. Bye-bye.